This design problem is about differential amplifier. Specifically, we'll use 10 kiloohm and 20 kiloohm resistors to design a differential amplifier. The design specifications are pretty clear from the problem statement. The desired differential mode gain is 2 for the design. A typical differential amplifier is selected as a prototype. V1 and V2 are the two inputs of the circuit. Let's say this is node A, and the voltage at node A is V prime. The current across Ri and Rf are I1 and I2 respectively. Then at node A, we could write out the KCL equation I1 is equal to I2. V2 minus V prime is the voltage drop across Ri. Divided by Ri, we get I1. Similarly, for I2, that is V prime minus 0 divided by Rf. There's only one single unknown from this equation, so we could solve for the only unknown V prime. Now let's look at the other part of the circuit. The voltage at node B should be also V prime. If the current across Ri is I3, based on Ohm's law, we'll have I3 is equal to the voltage drop V1 minus V prime divided by Ri. Look at the input resistance and the feedback resistance together. That is from V1 to Vout. Because the current into the negative input terminal is 0, we'll get I4 is equal to the voltage drop V1 minus Vout divided by the total resistance Ri plus Rf. Because both I3 and I4 are currents across Ri, I3 must be equal to I4. This will bring us a new equation. Substitute V prime into this second equation. We could solve for Vout. And the final solution for Vout is Vout is equal to Rf over Ri times the difference between the two inputs, V2 minus V1. As for the circuit design, we'll use Ri is equal to 10K and Rf of 20K. As for the differential mode, that is, the two inputs are not equal, the differential mode gain is defined as the output over the difference of the two inputs, which is equal to Rf over Ri. With the current components 20K over 10K, this is equal to 2 theoretically. When testing the circuit, we should be very clear about our signal lines. Where's V1, where's V2, and how the output is changing based on the inputs. In the next, I would like to show two different cases. Here's the first case. We ground V1, and we use a sine wave for V2. The scope shows both the non-zero input signal and the output signal simultaneously. Channel 1 is the input, the sine wave, and channel 2 is the output signal. And clearly, those two signals are in phase. Here's the amplitude of the two signals. In the second case, we switch the order of the two inputs. That is, V1 is the sine wave input, while V2 is grounded. Now let's look at the signals. The input and output signals are out of phase now, while keeping the magnitude of the signal pretty similar to the previous case. In both cases, the magnitude of the output signal is around 4.2 volt, and the difference of the two input signals is around 2 volt. This results in a differential mode gain of about 2.1. So both of our design specifications are met.